Okay, so hello everyone. Welcome to LICD lecture 41.3. Today we are going to discuss four different topics. That is, we will start with first order active high pass filter. We'll analyze the circuit, find its transfer function, and then plot its frequency response with the help of LT-spice and analysis. Second one is we'll solve a numerical on the same. That is the first order active high pass filter, and we'll verify the results in LT-spice. Third will be the first order active low pass filter and high pass filter, wherein the opamp is working in the non-inverting mode. Now, this is the most preferred mode of operation in case of filters. Then we'll design the first order active low pass filter and a high pass filter, wherein the opamp is working in the non-inverting mode. We'll follow up the design steps and verify the design values with LT spice. So without much further delay, let us begin with the topic. Now let me put it in the full screen mode. I think this will be fine. So what we will do is first we'll directly solve a numerical on this and then we'll come back to the theory. So let me go to the numerical first. So first of all, we will get it ready and then we will keep on coming back to this. Okay. So this is the numerical. You have your R2 as a feedback resistor. R1 and C1 values are given. So this circuit is behaving as an active first order high pass filter. That's what we have to verify. Okay, so the value of R1, C1, and R2 are given. So they have about to ask what is passband gain. We have to just derive this earlier. We will see this how this has come later. Right now we are using it directly. So R2 upon R1 is 5K divided by 1K, which is 5. And your in dB it will be 20 log to the base 5. That is 13.98 dB. And the cutoff frequency is given by 1 upon 2 pi R1 into R1 is 1K, C1 is 100 nanofarad. So this number will come out to be 1.59 kilohertz. And so this will be the frequency response. This filter will function as a high pass filter with a cutoff frequency of 1.59 kilohertz and a passband gain of 13.98 dB. So here it is. At low frequencies, it will reject, and after your F naught, that is 1.59 kilohertz, the filter will pass all the frequency with a constant passband gain of around 13.98 dB. Okay, so this is what we will simulate in LT Spice just now. Okay, so this is my circuit, and let me open the LT Spice. Yeah, LT Spice window is already been opened. So here the values of R2 is given as 5K, R1 is 1K, and C1 is 100 nanofarad. Okay, so let me expand this and let us simulate this circuit. So you can build this circuit in LT Spice very easily. So I'll go to simulate, I'll click on run, and I'll plot the frequency response. So as you can see, x-axis is frequency in logarithmic scale and y-axis is the gain. Let me check the values now. So this is the plot which I'm getting, and I need to check the passband gain. This is the passband over here. So the passband gain is around 13.97. Let's check whether it's matching with our results or no. Here, according to the theory, as per the theory, we are getting the passband gain was 13.98 dB, and here in LT Spice, we are getting the passband gain of 13.976 dB. That's very close. And now let's check the value of the cutoff frequency. Cutoff frequency will be 3 dB down, so it will be 10.976. So we'll go for 10.97. So I have to expand this to get the exact number. 0.97. 10 point. Yeah, it's now. Yeah, 10.97 dB, and we are getting the cutoff frequency nearby. Was actually little. Okay, yeah. So we are getting a cutoff frequency of 1.57 8 kilohertz and we were supposed to get 1.59. That's quite close, not a problem. So what happens is, this is what the graph will tell you. Above any frequency 1.57 kilohertz, the filter will pass those frequencies with a gain of 13.97 dB. And below this number, there is the cutoff frequency of 1.578 kilohertz. All the frequencies the high pass filter will reject. So basically, a high pass filter will pass the high frequencies above this cutoff frequency 1.578 kilohertz, and it will reject or attenuate all the frequencies below it. So let's also check. There was a concept of a roll-off rate for this. So it was 20 dB per decade. Let's check that number. So you have that 0 dB, 330 hertz, and let's check at 20 dB. Around 20 dB, it is 30 hertz. So 300, it's a jump of 20 dB. Okay, so for 20 dB, the frequency was around close to 30, and for 0 dB, it was close to around 300. You can check over here, it was close to 300 hertz, and for minus 20, it was close to 30 hertz. So when your gain rises from minus 20 to 0 dB for a 1 decade change in frequency, hence the roll off rate over here is plus 20 dB per decade. Now let us go back to our original derivation. Okay, so this was actually, it is indeed behaving as an active high pass filter, and the opamp is connected in the inverting mode. So this is similar to a differentiator circuit. Okay, and the opamp filters are designed for opamp operation in the linear region. I hope that is understood. Now let me open the window and keep it open. I'll use this. Yes, I'll keep this open so that it will be available for your reference. So this will act as a circuit, and the theory part I will be discussing on the left hand side of the PDF. I hope that's fine. Okay. Okay. So this is a linear application of op-amp. So analysis of inverting amplifier applies here also, correct? Because it is a linear application. So what will be Z1? Z1 will be a series combination of R1 and C, and that Z1 will be equal to R1 plus 1 upon SC1. That's what we have written over here. R1 is equal to Z1 is equal to R1 plus 1 upon SC1. And what is that? If you simplify SC, we will get Z1 as S R1 C1 plus 1 divided by SC. And the output of this, op-amp V out is given by VO is given by minus R2 upon Z1. Okay, and R2 value you can substitute directly. I mean, R2 value is as it is, and Z1 value you can resubstitute over here. So the final expression V out upon V in will be minus R2 into SC1 divided by SR1C1 plus 1. So this is my transfer function. So the transfer function is given by H of S, which is the transfer function of this first order high pass filter, which is given by equation number 1. It is minus of S into R2 C1 divided by 1 plus S into R1 C1. Okay. Now we can consider the H of S will be equal to R2. Yeah, we are multiplying and dividing by R1 over here in this expression number 1. What you will get? So H of S will be equal to minus R2 upon R1 into S times R1 C1 divided by 1 plus S times R1 C1. So this first term will, the negative sign indicates the phase shift introduced by the inverting mode op-amp, and the R2 upon R1 is my passband gain or DC gain. So and S R1 C1 upon 1 plus S R1 C1 represents the filtering action of high pass filter. Now we are substituting the passband gain as HOHP, with the mod of HOHP will be R2 upon R1, which is the passband gain, and your final expression for your transfer function gain of the system will be h of s is equal to HOLP into S R1 sequence by 1 plus S R1 sequence. This is the equation number 3. Okay. Now, if you substitute S equal to j omega in equation number 3, we'll get this. H of j omega is equal to HOLP into j omega R1 C1 divided by 1 plus j omega R1 C1, which we can rewrite as follows. H of j omega will be HOLP into j of omega upon omega naught divided by denominator will be 1 plus j of omega upon omega naught. So this becomes a equation number 4. Here omega naught is the cutoff frequency which is given by 1 upon R1. So F naught or F0 will be equal to 1 upon 2 pi R1. Now this frequency is called as the cutoff frequency or minus 3 dB frequency for a high pass filter. Now, equation number 4, if you want the magnitude of the transfer function, that is easily given by mod of h of j omega is equal to HOLP, the constant, into omega upon omega naught divided by under root of 1 plus omega upon omega naught the whole square. So that's the values. That's the value of this what we are getting, and this is the equation number 5. So the operation of your high pass filter can be verified from this equation number 5 very easily. Okay, so let us concentrate now. So for frequencies omega less than omega naught, that is low frequency, your omega upon omega naught will be lesser than 1. That means omega upon omega naught the whole square will be quite less than 1. So we can substitute 1 plus omega upon omega naught the whole square is approximately equal to 1. So if you put that over here, 1 plus omega upon omega naught the whole square is approximately equal to 1. You will get h of j omega, mod of h of j omega will be equal to HOLP omega upon omega. That's what, yeah, that's what we are getting over here. So, so the gain h of j omega is proportional to the input frequency omega in the low frequency range. Okay. So when you have very low frequency, the gain will, as you go on increasing the frequency for very low frequency, the gain of the system will go on increasing at a constant rate of 20 dB per decade. So that's what is happening. I have already informed that over here, the rate at which the gain increases with the gain of the increase in frequency, it's 20 dB per decade. And around omega equal to 0 hertz, the gain is very low. So ideally almost equal to 0, because if omega is 0, the gain will be very low. This means that as we decrease the input frequency, your gain will also decrease. So that's very evident from this equation. So for frequencies very low as compared to omega naught, the gain will keep on falling down, right? At a rate of the gain of the system will decrease actually, and as the frequency increases, the gain of the system will also increase reacting. Next point is at omega equal to omega naught, that is at cutoff frequency, a mod of h of j omega will be equal to HOLP into 1 upon root. Okay, now let us see this point. So if you substitute omega equal to omega naught, in the numerator we have this one, and in the denominator we have square root of 2. So that's why we get h of mod of h of j omega will be equal to HOLP into 1 upon root 2. That's what we are getting over here. Yeah, HOLP into mod of 1 upon root 2, where omega naught is the cutoff frequency. Well, in dB, at omega equal to omega naught, h of j omega will be 3 dB down of max value h of HOLP. So that's what we do over here. This maximum value over here is around, let's check that, around 30 point, around 13.97 dB. So when you go 3 dB down, it is around 10.97. Then only you get the cutoff. Okay. And for higher frequencies where omega is greater than omega naught, we can consider omega upon omega naught is very much greater than 1. 1 upon omega naught is square will be approximately equal to omega divided by omega 0, the whole square. So we substitute it over here. So in place of square root of 1 plus omega upon omega naught the whole square, we just have omega upon omega naught the whole square under root of it. So this term will get cancelled with the numerator term directly, and what is left out is HOLP. That's what we are saying over here. As the any for higher frequency greater than omega naught, your your mod of passband gain for a high pass filter, which is a constant value. So for omega greater than omega naught, we have a flat response. As you can see very clearly over here, this is the frequency response or uh, magnitude response of a high pass filter. As you can see, for the frequency less than omega naught, the gain is falling, down. And as the frequency increases, the gain increases at the rate of 20 dB per decade. That happens below omega naught. Now, once the system has attained the cutoff frequency, the system will keep the gain almost constant. So the constant gain is given by HP. Okay. The cutoff frequency is measured at 70.7% of 1 upon of HOHP. That is in dB, it will be 3 dB down. So in 3 dB down, you can mark the cutoff frequency. Similarly, over here, we have marked the cutoff frequency as 10.77. Yeah, around this point was my cutoff frequency. So this is the same dotted line which we have seen over here. So let's say this is my cutoff frequency. So below this, you see the nature of the graph is exactly the same. Okay, so this is after simulating the high pass filter, and this is what we have derived from the theory, from the equations also. So here it is. So how you can plot it theoretically? You can substitute. You have the formula with you. You can substitute all the values in dB, and you can calculate the frequency. Okay, so you will get this curve exactly as it is visible over here. Fine, we have seen that the roll-off rate is plus 20 dB per decade for the frequencies below omega naught. And after your omega naught for higher frequencies, the passband gain is remaining almost constant. So from year to year, this is my stop band. And from year to year, this is my passband. Okay. So this is about the frequency response of a high pass filter. And this is the summary, right? So this is my first order active high pass filter, which has a generalized transfer function as minus R2 upon R1 into S times R1 C1 divided by 1 plus R1 C1. Okay, so this is the high pass filter with a cutoff frequency of 1 upon R1 C1. That is F naught is equal to 1 upon R1 C1, which is called as the cutoff frequency or the 3 dB frequencies. So for frequencies omega greater than omega naught, the circuit will pass all the frequencies, and this range is called as a passband gain. Passband. And for frequencies omega lesser than omega naught, the circuit will attenuate the frequencies at the rate of 20 dB per decade, and the frequency range from 0 omega naught, this is omega naught, is called as the stop band. So that's what the description of your first order, high pass filter is. This we have already seen just now, that we got a cutoff frequency close to 1.59, and you get a gain passband gain of 13.98 dB. That's we already got it over here. Okay, so this circuit over here, which is given over here, this will function as a high pass filter with a cutoff frequency of 1.59 kilohertz and a passband gain of 5. That's what we have seen over here. Also, you can see clearly this is 20 dB per decade. That's the cutoff frequency, and this is the passband gain nearby around 14 dB. Now let us move on to the next topic. So we have already summarized this. Now, a very important concept coming up now, right now. Please pay attention. Let me just close this, and yeah, and let's keep the one. Let's open the design, one design, and keep it ready. Okay, this is the design. One very important concept we are learning. Actually, in reality, we are starting with first order low pass filter right now. Earlier circuit, whatever we have discussed was there, the opamp was in the inverting mode configuration. So from here on, your actual circuit, your first order low pass filter in reality will start. Okay, so here the opamp is working in the non-inverting amplifier, and as you can see, input is applied to your non-inverting terminal via R and C, and your RA and RB will decide the passband gain of this first order low pass filter. So anytime during the exams, if they ask you the analysis or the design of first order low pass filter, the opamp in the non-inverting mode is preferred. Why opamp in the non-inverting mode is preferred? Because when the opamp is in a non-inverting amplifier mode or a non-inverting mode, its input impedance is very much high. It's equivalent. It is equal to the input impedance of the opamp itself. So that's why we prefer this circuit. So you can use very high value of R without loading the circuit. Okay. So we have to concentrate on this now. From now on, we will concentrate on opamp as a non-inverting amplifier. Okay. So prior to this, we have done the analysis for the first order high pass and a low pass filter when opamp was in inverting mode. But now we have to do it for the non-inverting amplifier. So this is my circuit, which is RA, RB, R and C, and this is B plus, and here the current flowing inside is considered to be zero. Okay. So first order filter will consist of a single RC element network connected to the non-inverting terminal, that is the positive terminal of your op-amp. Okay, let me just put half screen. Okay, fine. So here your as I've already told you all, RA and RB will act as a will determine the gain of the filter in the passband. So from the circuit, what we can write is V plus. We are writing V plus in terms of VI. So if we consider the current flowing into the op-amp terminal, that is the plus terminal is almost zero. So what we can do is we can say that we can write V plus in terms of VI. So V plus will be V plus in terms of VI will be 1 upon SC divided by 1 upon SC plus R, right? Here what is we have written V plus of S will be 1 upon S into C divided by 1 upon SC plus R. That's what we have written, right? Yeah, into V of VI of S. So which we can simplify it as 1 upon SRC plus 1, right? V plus of S will be 1 upon SRC into 1 into VI of S. Okay, that's what we get. Now, since op-amp is in the non-inverting mode, so let's go back to the circuit. Since op-amp is in a non-inverting mode with the input V plus, so what's the output expression given by 1 plus RA into RB into, so again, 1 plus RA upon RB into B plus. Okay, let us observe that fact now. Here it is. B out of S will be equal to 1 plus RA into RB into V plus of S, since the op-amp is in the non-inverting mode. So from 1 and 2 equation, you will get finally output expression as 1 plus RA upon RB into 1 upon 1 plus SRC into VI of S. So what will be the transfer function H of S? H of S will be output upon input. So your H of S will be 1 plus RA upon RB into 1 upon 1 plus S into RC. So this equation number 3 is my gain of my system for a low pass filter, first order low pass filter. So here the first term, that is 1 plus RA upon RB, is my passband gain of a low pass filter, wherein HOLP will be given by 1 plus RA upon RB, and this 1 upon 1 plus S into RC provides the filtering action, that is a low pass filter. So if you substitute omega not equal to 1 upon RC in this, so you can rewrite this expression as H of S is equal to HOLP into 1 upon divided by 1 plus S upon omega naught. So this is the standard form of a transfer function for a first order. This is my standard form, equation number 4. Okay. So why first order? Because you have a linear equation upon S naught is linear equation, omega naught. Okay, so where omega naught is 1 upon RC and F naught will be 1 upon 2 pi RC, so which is the cutoff frequency. Okay, omega naught is my cutoff frequency. And equation number 4 is my standard form of transfer function for a first order low pass. So let us proceed further. So in order to determine the frequency response, we put s equal to j omega in equation number 4. So it becomes h of j omega is equal to HOLP into 1 upon 1 plus j omega upon omega naught. Okay. So you can easily substitute it as 1 upon 1 plus j f upon f naught, because omega is 2 pi f and 2 pi is a common term which you can eliminate, where f naught is given by 1 upon 2 pi rc. So if you analyze this circuit a little further, you will get such kind of a frequency response. So for frequencies lesser than f naught, your circuit will pass all the frequencies with a passband gain of HOLP, and for frequencies greater than f naught, your all your frequencies will get attenuate at a rate of minus 20 dB per decade, and your f naught is measured at 1 upon root 2 times HOLP, or 3 dB down. So this is a 3 dB down frequency. So this is my frequency response for a first order low pass filter. Let us quickly observe that over here. We'll come back to the design, but let us check the frequency response. So this is how the frequency response will look like. It is similar to what we have shown on the left hand side. Yeah, this one. So this frequency response and the frequency response we have obtained over here in LT spice are one and the same. Okay. And now let us analyze this further. So if I take the magnitude of this equation number 5, we'll get mod of h of j omega is equal to HOLP into 1 upon square root of 1 plus f upon f naught the whole square, which is equation number 6. So the observations with respect to equation number 6 are as follows. So at very low frequency, that is f is lesser than f naught, your mod of h of j omega will be HOLP. Now, how this is possible at low frequencies? We consider f to be very much greater, very much small as compared to f naught. So this entire expression I can rewrite as 1. So 1 plus f upon f naught the whole square will be approximately equal to 1. Hence, we can write h of j omega is equal to HOLP at low frequency. That's why we have written. So the low pass filter will pass all the low frequencies below f naught with a passband gain of HOLP. At f equal to f naught, your h of j omega will be HOLP divided by root, or 0.707 times HOLP. So how we got this? Just substitute f equal to f naught. So you will get 1 upon square root of 2 into HOLP. So that's what we are getting over here exactly. Now, for very high frequencies, wherein your f is much greater than f naught, so what you will have, so for very high frequencies, f is very much greater as compared to f naught. So this denominator expression will be square root of f upon f naught the whole square. So this term f naught will go up and f will come down. Okay, so it will be, let me just use the annotation. Let me draw it over here. So your okay, I need to clear this out. So what you will have h of j omega, that is a mod of it, will be equal to HOLP okay, HOLP into, if for frequencies f very much higher as compared to f naught. So if f is very much higher compared to f naught, what you will have in the denominator, 1 will be very much negligible. So it will be f upon f naught the whole square under root of it. So the formula will be given by as follows. It will be in the denominator, in the numerator we have f naught, and in the denominator we have f. So this is the formula. H of j omega will be equal to HOLP into f naught upon f. So as you can see, as the frequency increases, your gain of the system, that is given by mod of h of j omega, is reducing. So here what we can conclude is, as frequency increases, your gain of the system, which is h of j omega, okay, so h of j omega will reduce. So as the frequency increases, your h of j omega, mod of h of j omega decreases. So that's what we are doing over here. Okay. Now let's go to the next point. That's what we have written. Your h of j omega will actually, it will be very very small. That's why we have written very much less as compared to HL. But the real meaning is as I've explained before. So what are the observations over here from the analysis? So the observations are as follows. The low pass filter will have a maximum gain of HOLP at f equal to 0 hertz. Okay. So at low frequencies where f is around very very low, your maximum gain is around 0 hertz. Your maximum gain at 0 hertz will be HOLP. At f naught equal to, at f equal to f naught, the gain falls to 7.7 times the value of TDB down, the maximum value of HOLP. That's what we have observed over here. Okay, so at around f equal to f naught, your gain will fall down by 3 dB. That's what we have said. And for the frequency range 0 to f naught, it's called as the passband. For f greater than f naught, the gain reduces at a constant rate of minus 20 dB per decade. So this fall might be minus 20 dB per decade. And frequency range f greater than f naught is called as the stop band. Okay, so these are the few observations which we'll get from the frequency response of a, these are the few observations which you get the frequency response of the low pass filter. So again, I repeat, the first observation was for very low frequencies, that is f equal to around 0 hertz or lesser than f naught, your gain of the opamp will be constant, which is will be equal to the passband gain, which is given by HOL. And at f equal to f naught, your gain is HOLP by root 2 or 3 dB down. Okay, the range of frequencies from 0 to f naught is called as passband, and the range of frequencies greater than f naught are called as stop band. So basically, any frequency which is greater than f naught will be attenuated at a rate of minus 20 dB per decade. Okay, so this is called as a stop band region. Now let us continue. Now the next part was, we have to design a low first order low pass filter with a passband gain of 20 dB and 3 dB frequency of 500 Hz, and also protects the frequency response. Okay, so if we have given a choice to design a first order filter, please always go for a first order active op-amp low pass filter with op-amp operating as a non-inverting amplifier. So this is my circuit. Okay, so please follow this approach. The earlier one which we have discussed, the inverting amplifier, might have a problem of a loading effect because of finite input impedance. But this circuit over here will have a very high input impedance because op-amp in non-inverting mode is input impedance is much higher compared to the op-amp in the inverting mode. So whenever you're given a design of a first order filter, please prefer this design. Okay, so this is a very very important design. Okay, so let us begin. So this circuit will be consisting of RA and RB, right, which will decide the gain, and R1, C1 will decide the frequency, the cutoff frequency. So let us start. The passband gain is given by HOLP, which is 1 plus RA upon RB. We have seen that. We require a gain of 20 dB. So 20 log to the base 10 of 10 will give us 20 dB. That means 1 plus RA upon RB will be 20, will be 10. So RA will be 9 times RB. So let's say RB value is 2.7K. So RA value will be 24.3 kilo ohms. So if you select the standard value as 2.7K RB, and RA will be 24 kilo ohms, standard value basically. Okay. Now, the minus 3 dB cutoff frequency f naught will be given by 1 upon 2 pi R1 into C1, which is given as 500 Hz. So over here, R1 value we have to find out. So let's assume the value of C1 as 10 nanofarad. So R1, if you calculate in a calculator, that will be close to 0.83. Okay. R1 value you can substitute as 33 kilo ohms, a standard value. Now, for a first order low pass filter, the advantage of operating in non-inverting mode is that the passband gain and F naught can be evaluated independently. That's the biggest advantage of using in a non-inverting mode. As you can see very clearly, here the passband gain is 1 plus RA upon RB, totally different terms, and F naught is 1 upon R1 into C1. So that's the biggest advantage of using opamp in the non-inverting mode. The passband gain and F naught can be evaluated independently. Okay. So finally, your design circuit with all the standard values are as follows. So your RA, RB, RA is 24 kilo, RB is 2.7 kilo, R1 is 33 kilo, and C1 is 10 nanofarad. So this is my first order active low pass filter which I'm as a non-inverting. Okay. So let's just check this out now. Okay, we have already built this circuit in LT files. We have to just verify its response. Okay, so this is my circuit. As you can see very clearly, I have taken the values as it is because here if you do it on a breadboard and you will require standard values, so that's why I've taken standard values. But here I can take the values as it is. Any decimal number also I can take just for verification of design. So for the active first order low pass filter for non-inverting mode, the F naught was given as 500, passband gain was 20 dB. So accordingly, we got the values of RA, RB, R1, and C1. Now let us simulate it. It's already. So let's check the passband gain. It should be 20 dB, and it is 19.99, which is close to 20 dB only. Now let's check the cutoff frequency 3 dB down. So around 17 dB you get this cutoff frequency. So I need to expand this and adjust this close to 17 dB. So this number will be, yeah. So around 17 dB, the frequency is around 500 hertz. As you can see over here, that's the frequency which we have analyzed. Okay, so around 3 dB down, around 20 dB is 3 dB down, that will be around 17 dB. Here it is around 17 dB. The cutoff frequency is coming out to be 500 hertz. As you can see very clearly, you can see. Okay, so for frequencies lesser than 500 hertz, the circuit will pass all the frequency, and for the frequencies above 500 hertz, it will attenuate at the rate of 20 dB per decade. Now, now let's check that 20 dB per decade concept. So around 1 kilohertz, the gain is 12.66. Around 10 kilohertz, the the gain is around 10.6 kilohertz. Okay, so here it was at uh, at 1 kilohertz, it was around 1k. Yeah, it was around 13 dB at around 1k, and around 10k it is around. Okay, so you can check it out very clearly. You can check it out very clearly. That's not a problem. What you can check is you can check whether the gain is falling at the rate of 20 dB per decade. I hope that it is very small. It will fall at the rate of minus 20 dB per decade. So you can check this first. Okay, here you can check it. It is around 1.49, 9.9. Okay, around 10 dB. Here it is also around 15 point something. Yeah, it is falling at the rate of 20 dB per decade. That is correct. Okay, so this is how we check the frequency response for a designed first order active low pass filter. Again, I am repeating. If they ask you the first order low pass filter design in the exam, please prefer the non-inverting mode. Okay, so it will give you a lot of advantages. So that's what we have done. We have simulated this circuit and we got this response. The passband gain was 20 dB. The cutoff frequency was 500 hertz, and the roll-off rate was minus 20 dB per decade. That's the frequency response for a first order low pass filter with opamp in the non-inverting. So now let's quickly do the similar analysis. Now this will be similar. have done the active low pass filter. The first order active high pass filter will be very, very easy. So it just is that over here, everything remains the same, that RNC component has interchanged. That's it. So here the opamp is in a non-inverting mode. RA and RB will decide the passband gain. RNC will decide the cutoff frequency. So this is my first order high pass filter. So it consists of, let me just minimize a little. So it will consist of a filter with a single RC element connected to the non-inverting mode of non-inverting input terminal of your op-amp. So your RA and RB will decide the passband gain. From the circuit, what we have is over here, V plus in terms of VI, how we can write? So V plus will be equal to R upon R plus 1 upon SC into VI. So that's what we have written over here. So by simple voltage division rule, and we consider the current flowing into the op-amp terminal is almost negligible. So your bias current flowing into the non-inverting terminal we consider to be zero. That's why we can write V plus of S is equal to R upon 1 plus S into C into VI. Okay, that's what we write over here. Fine. So V plus of S will be simplified as SRC divided by 1 plus SRC into VI of S. That is the equation number 1. And also from the diagram, what is V out? So V out, it's a normal non-inverting amplifier mode, right? With the input as V plus. What will be V out? VO will be 1 plus RA upon RB into V plus, correct? So that's what we have written over here. Since the op-amp is in a non-inverting mode, VO of S will be 1 plus RA upon RB into V plus of S. So from this equation number 1 and 2, V plus, instead of V plus, we can substitute this. Okay. So what we get from equation number 1 and 2 is this. So V of S will be 1 plus RA upon RB into SRC divided by 1 plus SRC into VI of S. So what will be the transfer function? Transfer function will be V out upon V in. So it will be equal to, H of S will be equal to 1 plus RA upon RB into SRC divided by 1 plus SRC, where the first term will provide the passband gain and the second term will provide the filtering action. Okay, and the passband gain is 1 plus RA upon RB of your high pass filter. Now, if you substitute omega is equal to 1 upon RC, we can rewrite this equation number 3 as follows, which is the standard form also. So H of S will be equal to HP into S upon omega naught divided by 1 plus S upon omega naught. So this is equation number 4 is my standard form of transfer function for a first order high pass filter. Okay, we will proceed now because we have already done the similar analysis in low pass filter. We can quickly breeze through the high pass filter. So to determine the frequency response, we substitute S equal to j omega in equation number 4. So we get this equation, H of j omega is HOLP into j into omega upon omega naught divided by 1 plus j into omega upon omega naught. We substitute omega is equal to 2 pi f. So we can rewrite the expression pi as H of j omega will be HOLP into j of f upon f naught divided by 1 plus j into f upon f naught, right? So this is equation number 5, where f naught is given by 1 upon 2 pi RC, which is the 3 dB or the cutoff frequency of my signal. So if you see, the frequency plot will be like this. So for very low frequencies, for frequencies below f naught, all the frequencies will be rejected. So this is my stop band gain, stop band region from 0 to f naught. Above f naught is my pass band gain. So your filter will pass the high frequencies, whereas it will reject the low frequencies. Okay, where the maximum gain is HP, right? And around 3 dB down, you can check the value of f naught. At 3 dB down, you will get the cutoff frequency f naught. Okay. This is the frequency response for a first order low pass filter. If I go in the magnitude of this frequency response, so magnitude of H of j omega will be HOLP into f upon f naught divided by 1 plus f upon f naught the whole. So with this equation number, with the help of this equation number 6, we can plot this frequency response theoretically for all the values of frequencies and for all the values of gain. Very, very easy. Okay, so y'all can try it out later. But right now, let's focus on the 3 main points: when f is less than f naught, when f is equal to f naught, and when f is greater than f naught. What happens to the frequency response? So let's analyze this further. Let me just open up the design for a high pass filter, keep it simulated and keep it ready. So this was my high pass filter. So I wanted to show you all that frequency response. I'll come back to this later, but first let's check the nature of the graph. And around 500, 5000 actually. Around this will be the cutoff frequency, right? Yeah, yeah. So what are the observations with respect to equation number 6? What we get over here? Let me just clarify. Yeah. At very low frequencies, that is f is lesser than f naught, what will happen over here? For very low frequencies, f is less than f naught. So this term, denominator term will be 1 plus f upon f naught will be very, very less. So square will be even lesser. So denominator we can approximate square root of 1. So what we'll get is mod of h of j omega will be equal to HOLP into f upon f naught. And if your frequency is low, your h of j omega will be low. And this is very, very clearly mentioned over here. So that's why h of j omega at low frequencies, your gain of your system will be also will be very, very low. Okay. Again, I repeat, your mod of h of j omega will be HOLP into f upon f naught. Okay, just f upon f naught, because the denominator term is almost equal to 1. Okay, so for low frequencies, if h of for f equal to very, very low, your h of j omega will also will be low. Okay, they are directly proportional actually. The gain and the frequency are directly proportional for f less than f naught. For f equal to f naught, your mod of h of j omega will be HOHP divided by root 2. Let us check that. Yeah. So where f equal to f naught, this term will become 1 and denominator will become square root of 1 plus 1, that is root 2. So h of j omega mod of it will be HOLP divided by root 2. That's exactly what we get over here. Okay. For very high frequencies, that is f greater than much, much greater than f naught, what you will get is this. So if f is greater than f naught, your f square, f upon f naught, the whole square will be very much greater compared to 1. So denominator will have square root of f upon f naught the whole square. So this term in the denominator and the numerator will cancel out, and you will get h of j omega will be almost equal to HOL. Okay. So what we can deduce, what we can observe from this frequency response is that at very low frequencies, the gain is very, very low. At f equal to f naught, it is obtained at maximum value of HOLP divided by root 2. And for frequencies greater than f naught, you can have a pass band. So your high pass filter will pass high frequencies, whereas from 0 to f naught, it will reject the low frequency. So that's what we have written here. It has a maximum gain of HOHP at f greater than f, yeah, for f greater than f naught. At f naught, the gain falls to 0.707 times or 3 dB times the maximum gain HOLP. For frequency range, f greater than f naught is called as passband, and for the frequencies f less than f naught, the gain decreases at the rate of 20 dB per decade from f naught equal to 0. Correct? So from f naught to 0, the gain will reduce at the rate of 20 dB per decade. Okay, or you can say from 0 to f naught, the gain increases at the rate of 20 dB per decade. So that's the two way of saying the same thing. Now the frequency range from 0 to f naught is called as the stop band. Okay, so these are the various observations. Let's come to the design directly. So we have to design a first order high pass filter with a pass band gain of 10 dB and a minus 3 dB frequency of 5000 hertz, and also plot its frequencies. So this is my circuit of my first order active high pass filter. We have RA, RB, and we have C1 and R1 connected in this fashion. So here the passband given is as HOLP, HOHP is 1 plus RA upon RB, wherein the given value of HOHP is 10 dB. So 20, if you check it out clearly in a calculator, you will get 20 log to the base 10 of 3.16 is 10 dB. You can check the calculator. 20 log to the base 10 of 3.16 will give you 20 dB. That means what? 1 plus RA upon RB is 3.16. That means RA is 2.16 times RB. So let's substitute the value of RB as 10. So RA will be 21.6 kilo. That will be 22 kilo standard value. And now the 3 dB cutoff frequency is 5000 hertz. So F naught is 1 upon 2 pi R1 into C1. C1 you can consider it to be 1 nanofarad. So R1, if you calculate, you will get 31.83 kilo ohms actually. Sorry, the unit over here is wrong. I have written by mistake. So RA is 10 kilos. RA is 22 kilo ohms. By mistake, I have written over here kilo ohms. Very, very sorry for this mistake. RB is 10 kilo ohms. Your R1, if you calculate, it will be 33 kilo ohms. Okay, they're not kilohertz. By mistake, I have written it over here. So R1 will be 33 kilo ohms. Okay, so this is my design socket. So RA value is 22 kilo ohms, RB is 10 kilo ohms, R1 is 33 kilo ohms, and C1 will be 1 nanofarad. Okay, so this is my first order active high pass filter. Now let's check this design in LT files. Okay, so this is my circuit. So this is my active high pass filter design with a cutoff frequency of 5000 hertz and a passband gain of 10 dB. And these are my values. I've actually substituted the values as it is. I've not taken the design values. These design values are to be taken when you do it on the breadboard. So over here, the RA value and RB values we have taken as per the design, R1 and C1 as per the design. Okay. So let me simulate. Okay, I don't want a phase plot, so I'll remove it. Okay, so here is my frequency response. Now let's check the passband gain. The passband gain is around, if I increase a little the frequency, let's say I make it around 100. Okay, yeah. So the frequency over here, okay, let me make it as around, and let me simulate this once more. Okay, fine. Now let's check the passband gain. Passband gain should be around 10 dB. We are getting 9.85. That's fine. That's fine because this numbers which we have taken over here, 20 log to the base 10, 3.16, which we are getting, and RA and RB we got accordingly. So actually, it should be 21.6. Yeah, it's correct. Yeah, not a problem. So instead of 10 dB gain, we are getting a 9.85 dB gain. That's understandably reasonably well good value. Not a problem. So higher frequency, the passband gain is 9.85. Now let's check the cutoff frequency. So cutoff frequency will be 3 dB down. So it will be 9.87. So 6.87. It should around 6.87. You will have a 5 kilohertz frequency. Yeah. So around close to around around close to 7 dB. So it was supposed to be 10 dB. Around 7 dB around, you will get a frequency of 5 kilohertz, as you can see very very clear. Okay. So this is my cutoff frequency around 5 kilohertz, which I'm getting over here. So below this cutoff frequency, all the frequencies are rejected, and above it, all the frequencies are passed. So the frequencies above this are called as from this to this is called as your passband, and any frequencies below this 5 kilohertz are in the stop band region. That's the stop band and the passband for you. Okay, that's how we got it. So this was the design, and this is the frequency response. So the rate of fall is also 20 dB per decade. Here the gain is 500 hertz. The gain is 10 dB minus 10 dB, and the frequency is 500. Let's check at 100, around 100. So around 100 hertz, it's around yeah, the around approximately it's around 20 dB per decade. Okay, so you can check it out later. Not a problem. So this completes the design for your first active first order connected in the non-inverting mode. Please make sure whenever a design is asked, please follow only the non-inverting mode of operation. Okay, so I think we have covered this topic, And we have covered first of all the first order filter. Then we have seen explicitly the first order active low pass filter with opamp in the non-inverting mode. We have done the analysis. We have checked out the frequency response. And then finally we have done the design for both first order high pass filter and the low pass filter with opamp in the non-inverting mode. So I guess that's it for this lecture. Next time we'll begin with the band pass filters. Until then, have a good day.